Why does fire exist? Fire feels familiar. You've watched it dance on a candle wick, roar in a fireplace, hiss beneath a cooking pan. You strike a match, and suddenly there it is, bright, hot, alive. Most of us accept it without hesitation. Fire burns, fire heats, fire destroys, end of story. But if you pause and truly ask what fire is and why it happens, you uncover something far more remarkable. Fire isn't just a useful tool or a dangerous force. It's a doorway into the behavior of atoms, the flow of energy, the quiet work of sunlight, and the deep connections that tie living things to the air around them. Fire is not a thing, it's a process. And that process tells one of the most elegant stories in science. Let's begin with something ordinary, a piece of dry wood lying in the open air. The wood sits there motionless. The air surrounds it, full of oxygen. Both have been together for years, perhaps decades. And yet nothing happens. No heat, no reaction. Why not? Inside that wood are atoms of carbon. Floating freely in the air are atoms of oxygen. From an energy standpoint, carbon and oxygen prefer to be together. When they bond, the system becomes more stable and energy is released. That bonded state, carbon dioxide, is lower energy than the separated atoms. So why don't they instantly combine? Because nature places obstacles in the way. To form a bond, carbon and oxygen atoms must get extremely close. But as they approach, they initially repel each other. It's like trying to roll a ball into a deep valley that's hidden behind a hill. The valley represents the stable, low energy state. But the hill, the energy barrier, must be crossed first. Without enough energy, the ball rolls back down instead of falling into the valley. At room temperature, the atoms simply don't move fast enough. They collide constantly, millions of times per second, but they bounce apart again and again. No reaction, no fire. The system is stuck. This is why a piece of wood can sit in air for centuries without igniting. The atoms want to react, but they can't get over the barrier until something changes. When you light a match, you introduce heat. Heat is nothing mysterious, it's motion. Atoms begin to vibrate faster. Some move fast enough to crest that energy hill. When they do, carbon and oxygen snap together, releasing energy. That released energy increases the motion of nearby atoms. Those atoms gain enough speed to react as well. Each reaction triggers more reactions, and within a fraction of a second, the process explodes outward. That rapid cascade, that runaway chain reaction, is fire. Fire doesn't grow slowly, it erupts. One reaction becomes two, two become four, four become eight. Billions of atoms rearrange themselves almost simultaneously. Energy pours out as heat and light. This is why fire appears suddenly and spreads so quickly. It feeds itself. The heat produced makes further reactions possible, which produce more heat, which accelerates even more reactions. It's a feedback loop, sustained as long as fuel and oxygen remain and the temperature stays high enough. And the heat you feel. That's not a substance flowing into your hand. It's the chaotic motion of atoms transferring energy through collisions. Faster motion means higher temperature. Fire is simply matter vibrating violently as energy is released. Understanding this reveals something important. Fire isn't material. There is no fire stuff. Flames are glowing gases, energized particles, excited electrons. Fire is chemistry in motion. To extinguish it, you must break the cycle, cool the system, remove the fuel, cut off the oxygen, disrupt the feedback loop, and the process collapses. But this understanding opens an even deeper question. Where did the energy come from in the first place? To answer that, we must follow the wood backward, back before the fireplace, back before the forest, back before the seed. A tree looks solid, heavy, rooted in soil. It seems obvious that it grows out of the ground. But this intuition is misleading. If you examine where the mass of a tree comes from, the answer is surprising. It comes mostly from the air. Trees are built primarily from carbon, and that carbon enters through carbon dioxide in the atmosphere. Water contributes hydrogen and oxygen, and minerals from the soil supply trace elements. But the bulk of the tree's substance comes from gas. This was demonstrated centuries ago through careful experiments. Soil was weighed, a tree was grown in it for years, and then the soil was weighed again. The soil changed very little. The tree gained enormous mass. The conclusion was unavoidable. The tree did not come from the ground. It came from the air. But carbon dioxide is already a stable molecule. Carbon and oxygen are tightly bound together. Separating them requires energy. So how do trees manage it? They don't do it alone. Sunlight does the work. Photons streaming from the sun strike leaves and deliver energy. That energy is used to pull carbon dioxide apart, to separate carbon from oxygen. The oxygen is released back into the atmosphere as waste. The carbon is kept and assembled into sugars, fibers, and complex structures. This process, photosynthesis, is the reverse of fire. Fire combines carbon and oxygen and releases energy. Photosynthesis uses energy to force them apart. The tree stores that energy in its structure, locking it into chemical bonds. Every ring in the trunk, every branch, every splinter of wood is sunlight captured and held in place. When you burn a log, you are releasing that stored energy. The flame in your fireplace is ancient sunlight, collected slowly over years and released in moments. The warmth you feel once fell on leaves long ago. The light flickering in the fire is energy that traveled millions of kilometers from the sun, paused in the form of wood, and is now continuing its journey. Fire is stored sunlight escaping, and the story doesn't end there. The oxygen required for fire, the oxygen you breathe, also comes from plants. For billions of years, photosynthetic organisms have been breaking apart carbon dioxide and releasing oxygen as a byproduct. Early life found oxygen toxic. Many species vanished when it accumulated, but others adapted, learning to use oxygen as a powerful tool for extracting energy. That adaptation made complex life possible. Inside your cells, carbon-based molecules react with oxygen in a carefully controlled process called respiration. It is chemically the same as fire, but slowed, regulated, and harnessed. The energy released powers your muscles, your thoughts, your heartbeat. You are, in a very real sense, a slow, burning flame. When you exhale carbon dioxide, plants will eventually absorb it again. Carbon cycles, oxygen cycles, energy flows. Sun to leaf, leaf to body, body back to air. Fire is simply this grand cycle made visible. The glowing colors of a flame come from excited electrons dropping back to lower energy states. Different elements glow differently. Yellow, red, green, depending on their atomic structure. Smoke carries tiny unreacted particles upward. Ash contains the minerals that never came from the air in the first place. Nothing is lost. Matter rearranges. Energy transforms. And now, having followed fire from atoms to forests, from sunlight to breath, one question naturally remains. If all of this energy ultimately comes from the sun, what is happening there? Why is the sun so hot? Why does it shine at all? That is another story, one that begins deep in the heart of a star. And it's waiting for you when curiosity strikes again. So if all of this energy, every flame, every breath, every heartbeat, can be traced back to the sun, then the next question becomes unavoidable. Why is the sun able to give energy at all? What is happening inside that glowing sphere that allows it to shine relentlessly, day after day, year after year, for billions of years? At first glance, the sun looks like fire. It's bright, it's hot, it burns your skin if you stare too long. But the sun is not burning in the way wood burns. If it were, it would have run out of fuel long ago. Chemical reactions like fire simply don't contain enough energy to power something as vast as the sun for such an enormous time. Something far more powerful is happening. To understand it, we must leave Earth entirely and travel inward, deep into the sun's core, where matter behaves in ways that feel almost impossible. The sun is mostly made of hydrogen, the simplest atom in the universe. Each hydrogen atom is just a single proton with an electron buzzing around it. On Earth, hydrogen gas floats around quietly, rarely reacting unless you give it a spark. But the sun is not Earth. The sun is massive. Its gravity is overwhelming. That gravity squeezes the sun inward with unimaginable force. At the center, the pressure is so intense that atoms are crushed together. Temperatures soar to millions of degrees. At those temperatures, atoms no longer behave like familiar objects. Electrons are stripped away. Matter becomes plasma, a seething ocean of charged particles. Here, hydrogen nuclei are forced extremely close together. Normally, protons repel each other strongly. They carry positive charge and, like charges, push apart. Under ordinary conditions, no amount of persuasion would make two hydrogen nuclei merge. But in the sun's core, gravity and heat change the rules. The particles move incredibly fast. Collisions happen with tremendous energy. Occasionally, very rarely, two protons slam together hard enough to overcome their electrical repulsion. When that happens, something extraordinary occurs. They fuse. Two hydrogen nuclei combine to form a new nucleus. In the process, a small amount of mass disappears. That missing mass is not destroyed, it is converted into energy, exactly as described by Einstein's equation, E equals mc squared. Even a tiny amount of mass, multiplied by the square of the speed of light, produces an enormous amount of energy. This is nuclear fusion. Unlike fire, which rearranges atoms, fusion changes the nuclei themselves. It's a deeper transformation, tapping energy locked into matter at the most fundamental level. Each fusion event releases energy in the form of radiation. That energy pushes outward, fighting against gravity. This balance, gravity pulling inward, fusion pushing outward, is what keeps the sun stable, not collapsing, not exploding, just shining. And that energy takes a long journey. Photons created in the sun's core don't race straight to the surface. They bounce. They scatter. They are absorbed and re-emitted countless times. The trip from the core to the surface can take tens of thousands, even hundreds of thousands of years. Only then does the energy finally escape as sunlight racing through space at the speed of light. 8 minutes later, it reaches Earth. Some of it warms your skin. Some drives weather and wind. Some feeds plants. Some gets stored quietly in wood, coal, oil, and living tissue. And much later, perhaps decades later, perhaps centuries, it may return to the sky as fire. Seen this way, fire is not an isolated event. It's part of a cosmic chain that begins in the heart of a star. Now think about how astonishing this is. The energy that powers a campfire began as hydrogen atoms colliding in the core of the sun. That energy traveled across space, fell onto leaves, was captured molecule by molecule, locked into chemical bonds, and waited patiently, until a spark set it free. Fire is not destruction. It is release. And this idea, that energy can be stored, transformed, delayed, and returned, runs through all of physics. Nothing truly disappears. Energy changes form. This same principle explains why engines work, why electricity flows, why food fuels your body, and why stars shine. Different systems, different scales, same underlying logic. Now return to the idea of barriers, the hills that atoms must climb before reactions occur. In the sun, the barrier for fusion is enormous. Only extreme temperature and pressure allow it to happen. On Earth, the barrier for fire is smaller, but still significant. That's why wood doesn't ignite on its own. That's why gasoline can sit quietly until a spark appears. That's why your body needs enzymes to release energy from food safely. Nature is full of systems balanced on the edge, full of stored energy waiting for the right conditions. This balance is what makes the universe interesting. If energy barriers were too low, everything would react instantly. Matter would collapse into chaos. If barriers were too high, nothing would happen at all. No stars, no chemistry, no life. The universe sits in a narrow window where structure is possible. Fire exists because that window exists. And once you start seeing the world this way, everyday things become profound. A flickering candle is not just melting wax. It is a controlled chemical collapse, a visible echo of stellar processes. A reminder that the air around you is charged with possibility. Even your own body follows the same rules. Every step you take, every word you speak, every thought you think is powered by tiny reactions that resemble fire, but slowed, guided, and regulated. Oxygen enters your lungs. Carbon leaves your cells. Energy flows through molecular pathways instead of flames. You are not separate from nature's processes. You are one of them, and the same laws that govern stars govern you. Physics does not care whether the system is a galaxy or a grain of ash. The rules are the same. Only the scale changes. This is the quiet power of understanding. When you learn what fire truly is, you don't just learn about combustion. You learn about energy, matter, time, and connection. You learn that the warmth in your hands is tied to nuclear reactions millions of kilometers away. You learn that trees are built from air, that flames are sunlight returning home, and that nothing in the universe acts alone. Everything is linked. So the next time you see a flame, don't just see heat and light. See the long journey behind it. See atoms colliding, bonds breaking, energy flowing. See the echo of stars in a fireplace, the memory of sunlight in a spark. And if that makes you wonder what else around you carries stories just as deep, that curiosity, that urge to keep asking why, is where science truly begins. That curiosity, the simple act of pausing and asking why, is more powerful than it seems. Because once you allow yourself to wonder, the world stops being a collection of ordinary objects and starts becoming a network of processes. Nothing stands alone anymore. Everything is part of something larger, something unfolding. Fire is a perfect example of this. It feels immediate and local, right in front of you. But understanding it forces your mind outward, to forests, to ancient air, to the sun, and finally to the stars. A small flame becomes a lesson in the structure of reality. And that way of thinking doesn't stop with fire. It applies to everything. Take energy itself. We often talk about energy as if it were something that gets used up. But energy is never destroyed, it moves. It spreads. It changes form. When fire burns, energy doesn't vanish. It disperses into the surroundings, warming the air, radiating outward as light, increasing the random motion of molecules. This spreading is important. It points to a deeper idea known as entropy. Entropy is often described as disorder, but that word can be misleading. A better way to think of entropy is as the tendency of energy to spread out. Concentrated energy wants to disperse. Differences want to even out. Hot things cool down. Organized motion becomes random motion. Fire is a dramatic example of this tendency. A log contains energy packed neatly into chemical bonds. When it burns, that energy is released all at once and scattered into the environment. The system moves from an ordered state to a more spread out one. Entropy increases. And here's the fascinating part: life seems to do the opposite. Living systems create order. Trees build complex structures. Cells maintain organization. Brains form memories. At first glance, this seems to contradict entropy, but it doesn't. Life creates order locally by increasing disorder elsewhere. A tree grows by taking in low entropy energy from sunlight and releasing higher entropy energy as heat. It builds structure by exporting disorder. The total entropy of the universe still increases. Fire and life are not opposites. They are partners in the same energetic story. Fire releases energy quickly. Life releases it slowly. Both obey the same rules. This perspective changes how you see growth, decay, and even time itself. Time, after all, has a direction. We remember the past, not the future. Fires burn out, but ashes don't reassemble themselves into logs. The reason lies in entropy. Processes naturally move toward states where energy is more spread out, not more concentrated. That's why fire is irreversible. You can't gather the heat, light, and smoke from a burned log and turn it back into wood. The information about its original structure is lost, scattered into the environment. And yet, the universe is not dull or dead. Despite this constant drift toward equilibrium, complexity still emerges. Stars form. Planets cool. Life evolves. Minds arise that can reflect on all of it. How? Because the universe began in an extremely low entropy state. Early on, energy was unevenly distributed. Differences existed. Hot and cold, dense and sparse. Those differences made change possible. They powered stars, chemistry, and eventually biology. Fire exists because the universe is not finished yet. There are still gradients to exploit, still energy to move, still stories unfolding. And humans, in their own way, are participants in this process. When you light a fire, you are not breaking the laws of nature. You are cooperating with them. You are allowing energy to flow along a path it already wants to take. You provide the trigger, and nature does the rest. This is true of science itself. Science does not impose ideas on the universe. It listens. It follows clues. It watches what happens and asks careful questions. It looks for patterns that hold across different situations. Fire taught us about chemistry. Stars taught us about nuclear physics. Life teaches us about information and organization. Each insight builds on the last. And notice something important. None of this required believing in hidden forces or special exceptions. Everything follows from a few simple principles: energy conservation, atomic interactions, probability, and time. The beauty lies not in mystery, but in connection. The same equations describe a candle flame and a distant star. The same logic explains a burning log and a beating heart. Scale changes, but the rules remain. This is one of the most humbling discoveries humans have ever made. We are not separate from the universe. We are expressions of it. The carbon in your body was forged in ancient stars. The oxygen you breathe was released by plants. The energy that keeps you alive began as nuclear fusion in the sun. You are made of recycled matter, animated by borrowed energy, following laws written into the fabric of reality. And yet you can ask questions about it. That ability to reflect, to analyze, to wonder, is itself a product of the same processes. Consciousness arises from matter obeying physical laws, organized in just the right way. Which brings us back to education. Understanding science is not about memorizing facts. It's about learning how to see. It's about training your mind to look past appearances and search for mechanisms. Not just what happens, but why it happens. Fire looks simple, but when examined carefully, it becomes a lesson in energy barriers, feedback loops, chemical bonds, stellar physics, and planetary history. That's the power of asking honest questions, and it's why teaching matters. Good teaching doesn't give answers alone. It gives tools. It shows how to think, how to doubt, how to follow curiosity wherever it leads, even if the path winds through unfamiliar territory. Because once you learn to think this way, nothing remains boring. A glass of water becomes a study of molecular motion. A shadow becomes a lesson in light. A flame becomes a memory of the sun. And the universe stops being a backdrop. It becomes a conversation. So when you see fire again, whether it's a candle, a stove, or a distant star, remember that you are witnessing energy in transit, a transformation that began long before you noticed it and will continue long after it fades. Fire is not the end of something. It is a moment in a much longer journey. And that journey, from atoms to stars, from sunlight to thought, from curiosity to understanding, is still unfolding. And as long as there are minds willing to ask why,